All right, hey, so what's up, guys? All right, so continuing now from the last video in our journey to turn a busted K380 into a badass mechanical keyboard. If you haven't seen part 1 yet, you can check that out. But a quick rundown. I'm taking you from how I went from snagging this PCB from a K380 to making it so I could plug it into my own mechanical keyboard PCB. And I added knobs. So where we left off was, well, we had these encoders running from a circuit we built that used no microcontroller. But we realized that we could save way more energy, space, and cost, and even expand the capabilities by moving to the new Atmel Attiny Series 0, 1, or 2 chips. So that's what we're going to be doing today, moving the encoders over to an MCU, figuring out how to solve some hardware issues, and then an overview and testing of the new sleep and interrupt features we got with the new chip and the new Mega Tiny Core. So should you be using this new chip? And is this Mega Tiny Core any improvement over the regular Arduino core? Let's find out. All right, you guys ready? Okay, let's get to it. All right, so quick recap. How we set this up was we were using extra hidden buttons in the K380 PCB to activate key presses when we turned the encoder. And from there, we could set it to do whatever we want on our PC. So if we turn the encoder this way, it'll, for example, press one key, and if we go the other way, it'll press another. And we could use a center press for whatever too. Anyway, so another really big advantage of moving to an Arduino is that, well, in the last video with using a purely non-MCU circuit, well, I was about to add one big disclaimer, and that was a limitation of the K380 PCB. See, if we're using key inputs to run the encoder, we're limited by how fast the K380 can trigger the key presses and have our computer register them. So going back to the trigger pulses we were getting from our encoder from our final circuit, yeah, we were getting them all and closing and opening our photocoupler fast enough, but is it too fast for the K380 to be creating those key presses? Short answer, no. And yes. See, with normal use, yeah, it's perfectly fine, but going back to that jerk with anger issues, if you did flick the encoder like extremely fast, you could get it to trigger key presses too fast, and then you would miss some key presses. But again, you'd have to really be trying to intentionally do that. With normal use, you wouldn't see that. But, well, that would have been a compromise, and then you'd have to deal with that jerk in the YouTube comments saying how my stuff can't handle the spins. But now with an Arduino, we don't have to deal with that. We can guarantee that every detent pulse is sent over and registered on your computer. How? Well, because now with the Attiny, we got a working memory. So we could just read every trigger from the encoder and then just turn that into key presses set at the necessary press duration and interval. So even if it takes longer to create all our key presses than it does to turn the knob, then we're fine. Now, this could create a slight delay, but, well, how much? And how long do we actually need to reliably trigger a key press? And how long of an interval do we need between key presses? Well, I don't know. So let's find out. So here I just wrote a simple Arduino sketch running off an ESP32. It's hooked up to the K380 PCB, and it'll trigger a left option key press when I press this button. And I'll just adjust the length of the key presses and keep shortening it until we can't reliably trigger a key press anymore. I started conservatively at 500 milliseconds, and that was way too long. So kept going down and thought it was definitely bad at 5 milliseconds, but when I started recording, it was actually working reliably at 2 milliseconds. But it was, when I was first testing it, running only 95% at 5 milliseconds. So I'm setting it at 6 milliseconds to be conservative, and 6 milliseconds is actually pretty damn good, so I'm fine with that. If you want to play with it more, you're welcome to. Okay, so we got that. Now, how about the interval between key presses? So, okay, I just wrote another quick sketch, and when I press the button, it'll trigger the left option 5 times. Got the press length set to 6 milliseconds, and here I could just adjust how much of an interval there is between key presses. So let's start at 30 milliseconds. And, okay, got the 5 presses, so that works. Go to 20 milliseconds, and, okay, it didn't like that. Let's go 25. That's okay. Try 22. Okay, it doesn't like 22. Try 23. And also doesn't like 23. 24. Okay, so try a bunch of times, and that is going through. So 24 is consistent, but to be safe, let's set a little margin of error. 25 was fine, but I'm going to just set it to 26. And that'll give us 32 milliseconds per key press. That's pretty fast, and I'm totally happy with that. That's 31 presses per second. But again, you guys can play with it more if you want. Anyway, let's get back to the hardware stuff with the encoder and more problem solving. So I told you how important battery life is to me. And if we go to the datasheet of the encoder, we have this recommended filter circuit. Here we got 10K pull-ups and RC filters with 10K resistors and 20 nanofarad caps. This is to debounce a signal. You can check out this really good short video they made over at DigiKey about what a debounce is and why you need it. But the quick summary is When you turn the encoder, you're not getting these perfect off-on transitions. The metal contacts can actually bounce when they're closing or opening, creating these extremely fast on-off stutters. Let's take a look at what that looks like. So here I just got a 10K pull-up on the encoder and nothing else. And when I turn it, there, that's your bouncing. See how it's just bouncing on and off really quickly? Now we could make use of a software debounce, but I want to add a proper hardware one too. And we could just do what the datasheet recommends, but here's the thing. I mentioned in the last video how encoders are usually set up to always rest in the off state as it rests on a detent. But these coders aren't perfect. There might be a situation when they don't fall into that detent and end up in the middle resting in an on state. And that's not too super unlikely. So now that's fine with our microcontroller and our readings, but what that means is we'd have current running through these 10K pull-ups. So quick calculations with Ohm's law, and 3.3 volts divided by 10K is, so that comes out to 330 microamps, and that's for one brush. If they're both on, that's 660 microamps, and if you have the extreme bad luck of having both encoders A and B brushes resting in the on position, that's 1.32 milliamps. That'll drain our battery in no time, so we can't have that. So that takes us into a deeper dive of this RC filter circuit and how we can tweak it so we're not wasting energy for no reason. So basically how this RC circuit works is it takes time to charge and discharge this capacitor. So instead of the encoder brush just reading these crazy high-low, high-low, high-low pulses, if it was connected directly, the time it takes to register a low or a high comes down to how fast we can charge or discharge this capacitor. That time is how we can filter out anything that goes faster than the timing we set it to. So that brings us to the formula for the time constant. And again, other people do it better than me. If you want to watch a video that explains it, you could check out this one. But this is the formula. The time constant is equal to the capacitance times resistance. And that gives us a time in seconds. And it gives us a time when, while charging, how long it'll take to get to 63.2% of the voltage in. Why is there a formula that takes us to 63.2%? And why does it take us roughly 5 time constants to get us to a fully charged capacitor? Okay, so I had some complaints and jokes about how arbitrary this all is, but then I had to dig deeper, and there is a method to all this madness. And it all comes down to E, and Euler's number. You can check out this video if you want to learn more. It is surprisingly elegant, but it roughly comes down to how the charging and discharging of this capacitor isn't linear, but it follows a kind of very special growth pattern. It's kind of compounded. It's really interesting stuff, actually, so yeah, check out that video if you're interested. Anyway, you don't have to know all the specifics, and for our purpose, we'll just take the value this time constant gives us and be grateful we got it. Anyway, specifically, we're going to use the values at 2 time constants because that'll take us to roughly 86.5% of the voltage in. And our @tiny chip reads an input high at roughly 65% and a low at roughly 35%. Now going backwards, I wanted to set my pull-up as high as I could to get a reasonable current flow if it was accidentally left in the on state. So I thought I'd start with 1 meg. That would give me a current flow of 3.3 microamps when on. Then I thought I'd match that with a 1 nanofarad cap, which would give me roughly a 1 millisecond time constant. I thought that'd be enough, but when I checked on an oscilloscope, I could see that it wasn't fast enough to charge back up when I was spinning the encoder as fast as I could. So here you can see when I spin this as fast as I can, an on-off pulse is taking about 2.6 milliseconds. Now, I thought that'd work, but long story short, it wasn't fast enough. And as you can see here, it's not able to charge back up all the way. I mean, it works. I'm typing on that keyboard with those values now, but I want this thing to be solid. So it looks close, and it does look like we're getting to about 2/3, but that's not enough. So we went back to the data sheet, and well, with their suggested RC filter, we're looking at a time constant of 0.1 milliseconds. So going back to what our bouncing signal looks like, you can see here it settles down in like 24 microseconds. And at most, it was like 100 microseconds. And each stutter is like here 4.5 microseconds at most, but you can see the usual small ones are like under 1 microsecond. So if we go with the suggested time constant of 100 microseconds, none of these little on-off stutters at 5 microseconds will have enough time to get past that low threshold. Actually, no pulse under 100 microseconds will get through. And on our @tiny, we're only reading that falling edge on A, so we need to get high before we can register a low. And it's not going to be able to get high unless it's really high. And as for the state of B, we're reading it at the falling edge of A, so that should put us right in the middle of the state of B, in the middle where the brush is. So I'm going to go with the suggested time constant of 0.1 milliseconds. And by the way, I was just going to add another 1 meg resistor for the discharge, but you got to be careful there. You just can't use the highest value resistors you want. You start getting into some parasitic stuff, And when I checked with that setup, I was reading a high of 2.7 volts. So why? Well, I couldn't find it in the data sheet, but ChatGPT gave me a value of 10 megs to 100 megs for the high impedance inputs of the At-Tiny. So I can't say for sure, but my readings were matching if they were 10 megs. So that would have our two 1 meg resistors acting kind of like a voltage divider with the high impedance of the input. So anyway, I ended up just going with two 510K resistors and a 200 puff capacitor. That'll still keep us down to like 6.6 microamps per brush if stuck on. And it'll keep things fast enough to be able to catch every pulse, even if we spin the encoder as fast as possible. And let's not forget we got the option of adding a software debounce in our back pocket if we need it. Anyway, so this is what those values will look like in our RC filter. So as you can see, we got rid of all those micro stutters. So now it's just these clear on-off pulses. And if we zoom in, you can see that there is some stuff happening there where the stutters are trying to discharge and charge the capacitor, but they're happening too fast to effectively hit the thresholds of the lows and the highs. And that's why you use an RC filter. All right, so we got the hardware bits sorted. Let's see how it plays with the At-Tiny. And by the way, I hate calling this thing an At-Tiny. I have some old At-Tiny 85s lying around, and they were really limited. I never actually used any of them. So that's what I think of when I hear At-Tiny. But these new chips are like a completely different beast. I think I'll just call these Series 2s now, but that sucks because really there are 3 new classes for these chips. Series 0, Series 1, and Series 2, and the differences come down mostly to the flash and storage, the number of pins you need, and the ADCs and some other extras. But they're all very similar. Anyway, I went with the Series 2 because they're the higher end of the lot, with the most flash and RAM. And then I went with the one with the most pins. Could have went with just enough, but I'm guessing you guys want the option to add your own stuff. So I maxed things out. So there are 7 GPIO pins I left for you guys, and I left the default SPI and I2C pins alone, so you can do whatever you want with them. Anyway, other people went on about these chips, but let me just tell you why I'm loving them. First, they all got internal crystals now, just like the ESP32 S3s, so you don't have to worry about adding extra components. Second, the programming is easier with UPDI, so you don't need to add a UART chip. And yeah, it's not as easy as the S3s that have the USB stuff built in, and you are able to program the old Atmel chips with an FTDI board, but the new programmers are dirt cheap at like $3. And you can program these things if you have an old Arduino board, but support is limited, so I recommend just buying the cheap programmer. And buy 2 if you want to use the serial print and all that. All right, so let's test out what these fancy new chips can do when it comes to sleep and interrupts. So I wrote this simple sketch. When it's running, it'll just blink the LED, but after 5 seconds, it'll go to sleep. So when the LED is off, you know it's sleeping. Then I added an interrupt to this button, so when I press it, it'll wake up and then turn on a pin. And we can see how long it takes after I press the button for that pin to turn on. So let's upload it. Okay, you can see it blinking, and when it stops, okay, it's sleeping. So I got the output of the button on channel 1 on the oscilloscope, and the pin we turn on is on channel 2. So we can see how long it takes from when this button goes low, turns on, and the Atmel chip turns the pin on. So the documentation on the MegaTiny core is saying 8 microseconds plus 10 clock cycles. I'm running this at 5 megahertz. The chip can go up to 20 megahertz, but we save energy at 5 megahertz, and for our purposes, that's plenty. So if my calculations are correct, that would mean 1 clock cycle is 12 microseconds, so 8 is 96 microseconds plus 8 microseconds, and that should mean our pin should trigger 104 microseconds after we push this button. Okay, let's try it out. All right, ready? And now. So that gives us... Wait, what? Okay, let's try that again. Okay, my fault. I accidentally had this set to interrupt on a rising edge, so it was only triggering after I released the button. So that brings us to a cool new feature of these chips and the MegaTiny core. We can set the interrupts to trigger on the rising or falling edge, change in state, and a low. So let's change our code to set it to trigger on a falling edge, so the instant I press the button. And let's see how long it takes to wake up now. Okay, and my fault, my math was wrong. A clock cycle isn't 12 microseconds, it's 200 nanoseconds. So that's 0.2 a microsecond. So for 10 clock cycles, that should be 2 microseconds, plus 8 microseconds, so 10 microseconds. So what's going on? Not that I care, totally happy with 38 microseconds, but I guess it's just my code. So the wake continues at the point where it slept. So it's running through these lines of code, and that's taking cycles. All right, so let's see what happens when I put my interrupt handler right after where it sleeps. Okay, that's better, but that's still 29 microseconds. So back at the code, okay, we got this line that's taking a clock cycle. And oh, there's one more thing. One of the really cool things about MegaTinyCore is the improvements they made. Can't go on enough about this core. I really think it should replace the regular Arduino core. That's how awesome it is. So if you've used Arduino, and if you're watching this video, then like 98% you have, then you know of the illustrious digital write. Well, did you know that it's not optimized? So with MegaTinyCore, they added something called digital write fast, and that's at least 20 times faster. And they added this other stuff too, like digital read fast, pin mode fast, and lots of other stuff to dive into that just does away with a lot of the inefficiencies of the original Arduino core. And best part, this is all just added stuff. So they wrote the core so you could run your regular Arduino code and it'll just run no problem. But if you want to learn and take advantage of all this improved stuff, you can. So we can change this digital write to digital write fast, and let's see what happens. And now we're down to 19 microseconds. Still not 10, but yeah, I'll take it. Okay, and I messed around a bit more, and if I put digital write fast on the first line of the interrupt handler, I was getting 13 microseconds. But it's generally not a good idea to be running your code in that handler, I think. But, well, it gives you an idea what's possible with this thing. I'm sure I could get it down to the 10 seconds, but I'm totally happy with 19 microseconds. Anyway, I could make a separate video on MegaTinyCore alone, but I'm actually still learning it myself. But the links to the core are in the description, and the lead creator, I don't know him, but I can honestly say he's a superstar. But I'll just note on just one more thing that's revived my interest in Arduino because of this MegaTinyCore. So actually, when you mention you use Arduino, I think that's a bit frowned upon by the serious embedded systems people, like you're just a kid or a tinker, or worse, an artist. Some people have moved on to Python, but I really like C and C++, and I've been teaching myself how to write in straight C and C++. And yeah, this MegaTinyCore is like Arduino for adults. Again, you can do all the regular Arduino stuff, but this core exposes like a lot of the stuff under the hood, so you could get your hands dirty if you want. So let's take a look at how we set the interrupt pin. So it's this line here, and that's writing directly to registers. We're actually just writing actual bits to registers. So I'm not an expert on this myself, but I'm trying to learn, and it's great they just expose this stuff instead of hiding it and adding another layer to slow things down, but maybe make it more approachable to, well, beginners. And nothing wrong with being a beginner. Everybody starts there, but, well, I want to learn this stuff, and it's great I can get the opportunity to up my game. So, well, the documentation for this stuff is really pretty detailed. A lot's over my head, but if you just look at the examples, I think you can figure things out. And it tells you these are the bits we need to change, what to change them to, and how to do it. And if you want to learn more about manipulating bits with bitwise operations, I recommend this guy's video. Still trying to master this stuff myself, but he does a really great job of explaining things. Anyway, all right, this video is long enough, but I'll link the code on my GitHub down below, and you could even use this for your own encoder stuff you want to do. You can see I did separate the pulses of the encoder and the actual key press triggers. So here I'm just taking the pulses of the encoder and adding it to a counter, then using that counter to trigger the key presses at the specified press duration and interval. And testing it out, yeah, with normal use, there's no delay. And if you do want to go really fast, it's ever so slight a delay, as you can see here. And then I added short presses and long presses to the center buttons. I'll show you that in the next video and what we could do with it. And I'll show you the whole soldering everything up. And finally, what I did for the backlighting so we can save energy there too. And add routines to the RGB if you want to install them. And yeah, I'll be linking down below where I'll be selling these PCBs, but there are a few more tweaks and improvements I want to walk you through before I order the final PCBs. And yeah, aside from all the RGB stuff in the next video, we got a video after that where I went to the trouble of buying a power profiler kit too, so we can log the microamp currents flowing through this thing. And we can see if we can get all the power savings that we were promised. It's saying a sub microamp in sleep, or maybe sub 2 microamps, so we'll see if we can get that. And then there's another video where I walk you through the problems I had with trying to figure out how to get stabilizers on these Gateron low-profile switches. And no, they don't sell them. Not that fit on a regular PCB anyway. So we had to make our own. Anyway, all that to come. So if you're interested, like and subscribe, and I'll see you then. All right, guys, take care.